Hello everybody, welcome to the Math for Programming course. In this video, I'm going to discuss number theory for computer programming. So what is number theory? Number theory is the science of integers and their hidden patterns. It is really the backbone of many topics like cryptography, hashing, randomness, and efficient algorithms. The first topic to discuss is divisibility and prime numbers. So, what is the meaning of divisibility? Suppose we have two integers a and b, and we can say that a divides b, written as a followed by a vertical line followed by b. How can I say so? If I find that b equals a times k for some integer k, then I'm able to say that a divides b. That means when b is divided by a, the remainder will be just 0. So let us see this example. I would say that 3 divides 21 because 21 is equal to 3 times 7. And here a is 3, b is 21, and k is 7. So that means that 21 can be divisible by 3. And as another example, we would say that 5 does not divide 32 because we cannot find an integer k so that 5 times k equals 32. We can never find an integer k to satisfy this requirement. That's why we won't say that 5 divides 32. And another topic to discuss is the prime numbers. What is a prime number? A prime number is really a natural number larger than 1, with no divisors other than 1 or itself. So, is there any example? Yes, there are so many. We can pick 17 as an example. It is really a prime number because we cannot find other divisors that can divide 17 other than 1 and 17 actually. But 27 is not a prime number because I can find 3 times 9 equals 27. That means 3 divides 27 and 9 also divides 27. So we can say that 27 is not a prime number according to the definition here. What are the applications of divisibility and prime numbers? We can use them in cryptography. For example, we can use RSA, which uses large primes to make the code very strong. And we can also use prime numbers and divisibility in hashing. For example, we can use the prime-sized tables that can help us reduce the hashing conditions. So let us see how we can implement divisibility and the checking for a prime number in Python. So we have an example of checking for divisibility. I can write a function to check that whether a divides b. The idea is to use the modulus symbol here, b percentage a. If b is divisible by a, the remainder will become 0. So this feature would help us get the remainder when b is divided by a. Okay. So if the remainder is 0, I would say that a really divides b. Otherwise, I would say false. So let us see this example here. Does 3 divide 12? Yes, because we can say that 3 times 4 gives us 12. That means when 12 is divided by 3, I will have 4 and I have no remainder. I would say that 3 divides 12 and the answer would be true. So let me play with it. Yes, you will see true here. So 3 divides 12. Okay. And let us see how we can check for a prime number. So I can put a certain number into this function. So of course, a prime number cannot be smaller than 2. That's why if a number is smaller than 2, I would just say false. Okay. But if the number input is larger than or equal to 2, I have to do this check. I want to start with number 2. And then I would like to check for number 2, number 3, number 4, and so on, until we reach this number, which is meaning the square root of the given number that is input into the function. Because if we consider this upper bound, we would not do redundant checking for the possible factors that would divide n, okay? So if n divided by I has a remainder of 0, it means that I is able to divide n completely. That means we have no remainder. And if that's the case, I is really a factor of n. So if this situation exists, we would say that this n is not a prime number. I would just say false here. So I have to check for all the possible values of I from 2 to the value just below the square root of n. And if I have checked all these numbers, I'm not able to find an I, so that the remainder would become 0. I would say true here. That means that n is really a prime number. So let me check for these two numbers. Of course, 17 is a prime number and 25 is not a prime number, because we can find 5 times 5 equals 25. Okay, so 5 is also a factor of 25. So let me run it. Yes, you will receive true and false respectively, okay? So that means 17 is a prime number while 25 is not a prime number. Now, let's talk about another topic called modular arithmetic. Modular arithmetic is a system of arithmetic where numbers would wrap around after reaching a certain value called the modulus. It is just like the clock arithmetic. After 12 hours, the clock would reset to 1 instead of continuing to 13. So the possible values of the clock numbers would be just 1, 2, 3, 4 up to 12. It cannot go further to 13, okay? So let us see the real-life analogy of the modular arithmetic by using a clock. So suppose we have a 12-hour clock. If it is 9 o'clock now, what would be the time in 7 hours? Of course, you can just do 9 plus 7 to get 16. But for a clock, we cannot have 16 as the time shown on the clock, because we have a 12-hour clock. That's why we would just say 4 o'clock instead of 16 o'clock, okay? So we have to repeat the numbers that we used already. So let us talk about the meaning of the word modulo. Modulo here means the operation to find the remainder. So a mod b here is read as a modulo b, and it just refers to the remainder when integer a is divided by the integer b, okay? So the remainder of a divided by b is specified by the word modulo, okay? So let us see this example. 7 modulo 5 is 2, because 2 is the remainder when we divide 17 by 15, okay? And the other topic to discuss is congruence. What is congruence in modular arithmetic? It just means that two integers would have the same remainder when these two integers are divided by a fixed number, which is a positive integer, and the name is called the modulus. And we would say that two integers a and b are congruent modulo n if their difference is divisible by n. So let us see this elaboration here. A and b can leave the same remainder when they are both divided by n one by one. A divided by n gives us a certain remainder, and b divided by n would give us the same remainder as a does. Then we would say that a and b are congruent. Or we can use another way to explain the meaning of congruence. If a is equal to b plus kn for some integer k, then we would say that a is congruent to b under modulo n, okay? So we can write it as follows. A is congruent to b with modulo n, and it means that n can divide a minus b completely without leaving a remainder. Okay, so let us see the following example. We can say that 17 is congruent to 2 when we take the modulus as 5. The statement just says that 17 is congruent to 2 because the remainder is both 2 when 17 and 2 are both divided by 5 one by one. Okay, so in terms of the remainder perspective, 7 is congruent to 2 when the modulus is 5, okay? In another perspective, we can say that 5 divides 17 minus 2. That means it is just 15 here, okay? And this statement is true because 5 can really divide 15 completely without a remainder, okay? And another subtopic to discuss is modular inverse. The modular inverse called x of an integer a would need to satisfy the following condition. A times x is congruent to 1 with modulus m. if we can find out an x that satisfies this whole condition, we would say that the modular inverse of A would really exist. Okay, and if this condition is satisfied, then we can write x as A to the power of -1. So that means that x is the modular inverse of A. Okay, and if and only if the greatest common divisor of A and M is equal to 1, then we will say that the modular inverse would exist. When we see the word if and only if, it means that we can go from left to right, and also we can go from right to left. So it just says that if the GCD between A and M is equal to 1, that means if A and M are co-prime, then we would have a modular inverse of A. Or we can do it the other way around. If the modular inverse of A really exists, then we would be able to say that the GCD of A and M would just be 1. That means A and M would be co-prime, okay? So let us see the following example about the modular inverse of 3 with modulo M equals 7. So the first step is to check whether the inverse would really exist. I'm able to see that the GCD of A and M is equal to 1, okay? Because they are co-prime. Then we will be able to say that the modular inverse exists. So we can see the detailed steps here. Since 7 divided by 3 would be having a quotient of 2 and a remainder of 1. And then we can do 3 divided by 1, which is equal to 3, and we have no remainder here. That's why we would say that the GCD between 3 and 7 is 1, or that is coming from the Euclidean algorithm of division. So for this example, we would just say that 3 and 7 are co-prime. That's why the GCD between these two numbers would just be 1, okay? Therefore, the modular inverse would exist, okay? So let us go to step 2. We want to test the possible value of the modular inverse from 0 to m-1. Remember that m is 7, so we just check from 0 to 6. And the check is here. So I want to see when I multiply a by x to get a number, is that number possible to have a remainder of 1 and when it is divided by m, which is 7 in my case? Let us see here. So if I check for x equals 0, I will have 3 times 0 equals 0, and that number would have a remainder of 0 when it is divided by 7. Okay, so how about x equals 1? If a times x is now 3, and this 3 is divided by 7, the remainder of 3 divided by 7 is just 3. So it is not 1 yet, okay? So how about x equals 2? When I multiply a by x to have 6, I need to check for the remainder when 6 is divided by 7. And you will see that the remainder is still 6, so it is not equal to 1. So how about x equals 3? When x is equal to 3, a times x is now 9, and 9 divided by 7 is of course having a remainder of 2. It is not 1 yet. How about choosing x equals 4? When x is multiplied by 4, the answer would be 12, and 12 divided by 7 would have a remainder of 5, which is not equal to 1 yet. So let us try another value of x. When 3 is multiplied by 5, I would have 15, and 15 divided by 7 is really able to return a remainder of 1. That's why x is 5. I mean the modular inverse of 3 is just 5. Okay. And this modular inverse would refer to the modulus of 7. Okay. And of course, if you want to check for one more x like number 6 here, you will see that the product of a and x, which is 18 here, isn't able to get the remainder of 1 when it is divided by 7. Okay. So the remainder is actually 4. That means we have only one possible value of x that can be the modular inverse of a, okay? So let us see the applications of modular arithmetic. We can use them in cryptography, say the RSA decryption. We can also use modular arithmetic in hash functions, and we can also use modular arithmetic in computer graphics like the color cycling process, okay? So let us see how we can implement modular congruence and modular inverse in Python. So the first part to discuss is the modular feature. So it is just easy. I can get the modulus when I use the percentage sign here. So when A is divided by B, I'm able to get the quotient as well as the remainder. And I can use this percentage symbol to get the remainder when 17 is divided by 5. So of course the value would be 2. Yes, it is just 2. It means that the remainder when 17 is divided by 5 is just 2, okay? And I can check for congruence of A and B with modulo m. So I can make a function to put A, B, and m into the function parameter. And according to the definition here, I can just need to check whether A minus B divided by m would have a remainder of 0 or not. So we are talking about this definition, okay? Or this part, okay? So if A minus B divided by n would have a remainder of 0, it means that A and B would be congruent with modulo m, okay? So let us see here. I want to see whether A and B would be congruent if the modulus is 12. So that's why I can put 17, 5, and 12 into the function. And I'm able to show that it is true. Yes, it is really true because 17 minus 5 is 12, and of course 12 divided by 12 is 1, and the remainder is 0. That's why this condition is satisfied, and I have true as the answer. And here, let us talk about the modular inverse. So I can write a function to check for the modular inverse by providing the number as well as the modulus to consider. So it is essentially implementing the previous example that is shown on the notes, which is this part here, okay? So I need to check from 1 to the number just before the modulus, okay? That's why I would just check from 1 to 6, okay? And the first case isn't necessary because when I is really 0 here, the modulus is of course 0. That means the modulus is not allowed to be equal to 1 when x is 0, okay? So the modular inverse can never be 0, okay? And I just need to check for this condition, A times I percentage m or modulo m is equal to 1 or not. If it is equal to 1, then I would say that I'm able to return that modular inverse. If I'm not able to satisfy this condition when I have checked for all the possible i's here, then I would say that there is no modular inverse for a particular number, and the absence of the modular inverse is possible. So let us run the program. Yes, you will see 5 here. That means the modular inverse of 3 is just 5, okay? And now let us talk about greatest common divisor, which is the third part of the video. And I'd also like to introduce the meaning of LCM. So what is GCD? GCD is just the greatest common divisor, which is actually the largest number that evenly divides 2 or more integers without leaving a remainder. That means I would say that the GCD is the largest possible number that divides 2 or more numbers, okay? So for example, if we have 2 numbers, say 12 and 18, the GCD is just the biggest number that divides both 12 and 18, okay? So we can check for the factors of 12 and 18 to see that we have such common factors, 1, 2, 3, and 6. And the greatest possible common factor is just 6. That means the GCD between 12 and 18 would be just 6, okay? Instead of listing out all the factors of the 2 numbers, I can use the Euclidean algorithm of division to help us find out the GCD more efficiently. Okay, so how can we do so? Let us go to the algorithm here. Suppose we want to find out the GCD between A and B, where A is larger than B and both of these numbers are larger than 0. So let us go to the first step. We have to divide A by B to get the remainder. Okay, so when A is divided by B, I can say that A equals B times Q plus R, where Q is the quotient of the division and R is the remainder of the division, okay? And then I can replace A with B and B with R, and then I go back to step number 1. I would need to repeat 1 and 2 until the remainder becomes 0. If that's the case, the last non-zero remainder is the GCD. Is this a bit abstract? I think so, so let us go to an example. So I would like to say that the Euclidean algorithm of finding out the GCD is essentially implementing the following modular arithmetic. I can just find the GCD of AB, which is equal to the GCD of B and A modulo B, okay? So suppose I have 252 and 105 here. I want to find out the GCD between these two integers. The process is like that. I want to apply the Euclidean algorithm. So I would need to do 252 divided by 105 to get 2, and the remainder is just 42. Therefore, I can write 252 equals 105 times 2 plus 42. Okay, and now I pick up this number, which is the original B, and this number, which is the original remainder, to become A and B respectively. So you will see that 105 divided by 42 would be having a number of 2 as the quotient and 21 as the remainder. So I'm able to say that 105 is equal to 42 times 2 plus 21. So now I would like to pick up 42 as A and 21 as B. So you will see that when I do the division of these two numbers, I'm able to get 2, and the remainder now is 0. So when the remainder is 0, I will just stop, and I'm able to say that 42 is equal to 21 times 2 plus 0. And you can see that the last non-zero remainder is just 21, which is this one. After this remainder, I will have a remainder of 0. Okay, so the last non-zero remainder here would be just the GCD between 252 and 105. Okay, and let us talk about the meaning of the least common multiple. The least common multiple, LCM, is the smallest possible number that is a multiple of 2 or more integers. Okay, so let us see this example, LCM of 4 and 6. I can just list out all the factors of 4 and 6 respectively. And I'm able to see that, when I have 12 and 24, I'm able to show that these numbers are really the common multiples of 4 and 6. That means 4 and 6 would have 12 and 24 and so on as their common multiples. Okay, so the least common multiple is just the smallest number in the multiples. That is just 12 in this case. Okay, so we would say that the LCM of 4 and 6 is just 12. Okay, and actually, if we know the GCD, we can use it to find out the LCM. The LCM is just equal to the product of A and B, which is going to be turned to be positive by using the absolute value sign, and then I divide that number by GCD of A and B. So we can use this formula to find out the LCM if we already know the GCD. Okay, so what are the applications of GCD and LCM? We can use them in cryptography, like the RSA algorithm. GCD is really essential in public key cryptography that is performed by the RSA algorithm. And we can use GCD and LCM in modular arithmetic and hashing. The GCD can help us in simplifying the modular expressions, and GCD can help us avoid the collisions in hash functions. Okay, and we can use GCD and LCM in task scheduling. LCM is used to find the least time after which periodic tasks, like interrupts or processes, will align again. Okay, and for parallel computing, we can also use LCM. LCM can aid in coordinating tasks across multiple processors that would operate at different speeds or intervals. Okay, so let us see how we can implement GCD and LCM in Python. So we can use the Euclidean algorithm to find out the greatest common divisor. So if this B is not 0, I need to do the division to see the remainder, and this remainder will be replacing the original B, and the new B will be replacing the original A. So we do this kind of process until this position here is 0. If that is 0, the while loop would end, and I'm just able to return A here as the answer to the GCD. Okay. So for example, if 48 and 18 are put into the function, I'm able to find out the GCD of these two numbers as 6. Yes, it is 6. So it means that the largest possible common divisor of these two integers will be just 6, okay? Here we can go to the least common multiple. We can use the definition of the least common multiple by using the GCD. So the absolute value of A times B is going to be divided by GCD to see the quotient if A and B are both larger than 0, okay? So I have to use this part here to check for the sign of A and B. If A and B are both positive, then the LCM can really be defined and they will be just output to the display, okay? If I'm not able to show that A and B are both positive numbers, then the GCD would just be 0, okay? So let me try to see the LCM of 12 and 18. Yes, I will have 36. That's why I would say that the LCM of these two numbers would be just 36, okay? And now let us talk about Fermat's little theorem. If P is a prime number and A is an integer not divisible by P, that means if A and P are co-prime, then we would say that A to the power of P minus 1 is congruent to 1 with modulus P. That is the meaning of this theorem, okay? The condition to use this theorem is that A and P would have the greatest common divisor as 1, okay? And equivalently, A to the power of P is congruent to A with modulus P. And this statement would hold for any integer A, even if P divides A, okay? So this format is a bit more lenient than the previous one, okay? And if P divides A, then both A to the power of P and A are both divisible by P. Therefore, both A to the power of P and A are essentially 0 modulo P, okay? So A to the power of P and A are both congruent to 0, okay? So let us see this example. If P is 5 and A is 3, I can play with the Fermat's little theorem. Since P equals 5 here is really a prime number, and A equals 3 is not divisible by P equals 5, I can say that this very first one would hold, and I can verify it as 3 to the power of 4 equals 81, which is congruent to 1 when the modulus is 5, okay? Since 80 is divisible by 5, and 81 is not divisible by 5, and it will have a remainder of 1 when 81 is divided by 5, okay? So alternatively, I can use the second one here. 3 to the power of 5 equals 243, which is congruent to 3 when the modulus is 5, okay? So I can check for the Fermat's little theorem if I have both P and A given, okay? So how can we apply the Fermat's little theorem? We can apply them in two situations. We can apply this theorem in the fast primality testing, which is the basis of the Miller-Rabin primality testing. And we can use the Fermat's little theorem in the fast exponentiation in cryptography. And let us see how we can implement the Fermat's little theorem in Python. Now let us see the following function. I want to put A and P into the function, and I want to see whether P is a prime number or not. If it is not a prime number, or if P is less than or equal to A, I would return false. That means the Fermat's little theorem would fail in this case. And if the condition here fails, I would go to the other part here to return A to the power of P minus 1 with modulo P. And then I would like to put A, P minus 1 and P into the POW function. The first parameter is just the base, and the second parameter is the exponent, and the third parameter is just the modulus. So I would like to see whether A to the power of P minus 1 modulo P would be equal to 1, okay? If that's the case, then the Fermat's little theorem would be applicable to my choice of A and P, okay? So I would like to say here, A is 2, P is 7. So I would like to check whether 2 to the power of 6 is congruent to 1 with modulo 7. Okay. It should be true because 64 is essentially congruent to 1 if the modulus is 7. Okay. 64 divided by 7 would have a remainder of 1. And 1 divided by 7 would also return a remainder of 1. Okay. So I can use this POW function to check for the Fermat's little theorem when I have the A and P given. Okay. The final topic to discuss in this video is the Sieve of Eratosthenes. The Sieve of Eratosthenes is an ancient and efficient algorithm for finding out all the prime numbers up to a given integer n. So here are the steps involved. We need to create a list of integers from 2 to n, and they are all unmarked initially. And I would like to cross out some composite numbers from this table so that I will have the prime numbers remaining in the final step. Okay, so we start with the first prime number, which is of course 2, and then I would like to mark multiples of p, starting from the number p squared, and all these marked numbers are actually the composites of p. Okay, so in this way I would cross out p squared and then p squared plus p and then p squared plus 2p up to n. Okay, so I'm able to remove the multiples of p starting from p squared in this way. And then I would like to mark the next unmarked number, which is greater than p. So this will be just the next prime number, and I would like to set p to this number. And then I'm going to repeat steps 3 and 4, okay, until p squared is found to be larger than n, which is the final number to reach in my list. Okay, and the remaining unmarked numbers are just the prime numbers up to the given number n. Okay, so let us see this example. I want to find the prime numbers up to 30. Okay, so n is 30. I just list out all the numbers from 2 to 30 in the first step. Okay, and then of course 1 is not a prime number. It can be ignored in the sieving process. That's why this box is empty. And then I want to remove multiples of the first prime number, which is 2. And the starting point is p squared, which is equal to 4. So you can see that 4, and then p squared plus 2 is 6, and then p squared plus 2p is 8, so on and so forth. And I'm able to remove p squared plus other multiples of p. Okay. And then after removing the prime numbers with p equals 2 initially, I'm able to remove multiples of the next prime number, which is p equals 3. And I will start from p squared equals 9. So the first number to remove is 9, and the second number to remove is 9 plus 3, which is of course 12, and 12 is already removed in the first step. Then we would like to remove another number, which is equal to 2 squared plus 2p, which is 9 plus 6, which is equal to 15. And the next number to remove is p squared plus 3p, and then the next number to remove is p squared plus 4p. Okay, so we do this process until we reach the final number 30. Okay, if the number is already removed in the previous step, we just skip that position and we go to another number that is yet to be removed. Okay, and the next multiple to handle is the next prime number, which is p equals 5. So we start with p squared equals 25. So I just need to remove 25 because p squared plus 1p is 30, which is already removed. So I don't need to handle that removed number. And for another multiple to go, it is just p equals 7. And we need to start with p squared equals 49. But we know that p squared is now larger than 30. That's why we would just stop the sieving process. And the numbers remaining in the final step will just be the prime numbers up to 30. Okay. So how can we apply the Sieve of Eratosthenes in finding out the prime numbers? We need prime numbers to handle cryptocurrency. That's why we need to use some ways to find out the prime numbers. And we can also use the Sieve of Eratosthenes in factorization to find out the possible prime numbers that can help us ease the factorization. And let us see how we can implement the Sieve of Eratosthenes in Python. So here is the code of the Sieve of Eratosthenes. So I'll write down a function here. So the first step is to make up a very long list to assume that all the integers before n would all be prime numbers. Okay, so I will say true until we reach n. Okay, and of course we know that 0 and 1 cannot be prime numbers. That's why I would set them as false explicitly. Okay, and then I want to check for 2, 3, 4 and so on until we reach n. Okay, so I need to check for prime numbers. So I need to check for each of the numbers from 2 up to the square root of n, which is the efficient way of checking for the prime numbers by checking up to this upper bound. Okay, so if the position corresponding to this given number I is already storing the true value here, I would like to see whether that position corresponds to a prime number or not. So I will go to this for loop and I pick up this I to check for I squared, and then I need to have a jump by I, which is the step size to simulate p squared plus p, and the final stage is n minus 1, so we reach n at most. Okay, and if I is really a prime number, I would like to claim that for all these j's, they are really not prime numbers. Okay, and then I repeat the process for other i's, and I just do p squared plus p or I squared plus I repeatedly to do the removal of the numbers from the list. And I'm just required to return the corresponding numbers when the is prime value here is true. Okay, so I will just leave the prime numbers in my answer. So let me see the prime numbers up to 30. And you will see that I will have these numbers as the prime numbers before 30 by using the Sieve of Eratosthenes. Okay, so this video has discussed many topics about number theory for computer programming. We handled divisibility and prime numbers. We also handled modular arithmetic. We also learned the meaning of congruence in modular arithmetic. We also learned the modular inverse and the way to find that out. We also learned the meaning of the GCD and LCM. The way to find the GCD is the Euclidean algorithm. Okay, and the LCM can be evaluated by using the GCD. Okay. Also, we discussed the Fermat's little theorem to see whether A and P would satisfy this theorem by checking the congruence shown here and here. Okay. And finally, we discussed the Sieve of Eratosthenes, which is a way to find out the prime numbers that are smaller than a given number called n here. And the steps are shown explicitly in the tables shown here. This is the end of the video. If you have any questions about my video, please leave your questions on the comment section below the video. If you like this video, please give me a like and please subscribe to my channel. Thank you for watching.